Hello and welcome back. So far we have taken the data set and splitted the data into train test, and using train set we did EDA and feature engineering, and we fixed the quality issues, we fixed nulls, and then we did some feature engineering, or we converted our categorical counts to numbers using label encoding. Now the data set is ready. We are at this stage, and we are going to feed the data into the AML algorithm. Right? Before we feeding, we'll split the data into x and y, the x variables and the y variables, and then the model is ready. We'll test it with the train set and test set, and then look at the accuracies and all the stuff. We'll see that whole thing now. Let's jump back to the code. So here we have got the data set ready, right? So we need to take the input variables. So what are all the input variables? Which are not salary. The column salary is the output variable, and the rest of the columns are all input variables. That can be extracted using a list comprehension. What is list comprehension? For x in the train set columns, till that, right, what it will do? All the columns one after the other it will take. If x not in salary, we are trying to extract it and put it in a list. So when I execute this, right, I'll get all the columns which are not salary. Okay, I got all the columns which are not salary. Those are nothing but input features. So we need to split our train set into x train and y train. The scikit-learn algorithms will actually take the x separately and y separately. So we need to split the data vertically. So we are splitting that x train and y train. When we say data frame.loc and then colon, that means all rows, and comma, we specified all the columns we wanted. Okay, so that means you will get all rows related to these columns. That's the train set x, the input variables of x, and then only the salary, the series object, is going to be the y, right? So we need to pass these to linear regression algorithm. So let us execute this statement, and then we can execute the linear regression. But you can actually replace this these column names in a list object with this list comprehension also. I don't know whether you're getting it or not, but try to experiment and see. Right? You can do that way also. Both are same. Okay. So I have taken the linear regression algorithm, and then I am passing the x train and y train. We have taken all these columns values for all the train set data, and the salary values for train set data, and specified, saved them, or kept them in two variables called train x and train y. We are passing it and we are training it. When you say fit, that's when the training happens. What is training? It is going to form the equations and then solve all of them at once and find thetas. That's the training, right? We have seen it in simple linear regression, right? So now the model is ready. Till this place it is algorithm, just an algorithm. Once you said fit, the statement got executed, it became a model because it has got the equation. Whether you pass 1500 records or 15 million records, it's going to get one equation. So the equation is going to be present in this model, and we are using predict method and passing all the x train. If you look at this diagram, once the model is ready, you are passing only x train because it is going to predict y cap, and the y cap is going to be evaluated. If the model is working good on the train set, we will actually move to the next step and test it on test set also, the unseen data. So I passed x train and made predictions. The predict method will predict the y cap values. Now we have y cap and y, right? Y is in train y, the y cap value in train prediction. Now I can calculate the metrics, the R2 score and mean squared error. We know R square score, right? That is actually already present in the scikit-learn's metrics method. Right? The metrics method will give you this method, and you can use that method to calculate. So the R2 score method will take train y, or y and y cap. When you pass y and y cap, it is going to calculate the RSS and TSS and subtract RSS from TSS and divide by TSS. That whole thing right? So it's going to calculate the train R2 score and train MSE, mean squared error. Mean squared error is what? Y minus y cap whole square divided by m, sigma I is equal to 1 to m. For each row, it is going to calculate the residual and square it, sum it, and take an average. So these two were calculated here. Let me execute the predict statement, and then let me execute this statement to import the R2 score and the mean squared error and the accuracy scores. The R square score got only 62%, and this is not a good model, or the model did not understood well. Only 62% means it is not so well. And if you look at root mean squared error, it is actually saying 11,775. That means on an average, the error is oscillating around 11,775. Maybe it is predicting 11,000 more or 11,000 less. Okay, so in the algorithm we used is linear regression. It is based out of an approach called as normal equation. That's a linear algebraic approach, and there are no hyperparameters to tune, or there is nothing we can tune in there. So let us try to see, because of that reason, let us try to see how is it working on test set. We know that model is underfitted. When the model is underfitted, we will not move to the next step and try to test it on test set. But there is nothing we can do with this particular algorithm. So we are moving to the next step and trying to test it on test set, and how is it working, whether it is overfitted or not, even this underfitting level, whether it is overfitting or not. What I mean to say is, I've got 62% on train set, but when I test it on test set, if I get 40%, right, it is overfitted. Model is underfitted on the train set, and overall it is overfitted. So algorithm did not understand anything proper. So let us try to see how is it working on test set, right? So unseen data. We have kept some data aside and we are trying to test it. Before we test it, we need to apply all the transformations we have applied on the train set. What did we do? We have replaced all those values, where the lines of code is less than 0, we replaced it with 0. That is one thing we did in train set. We need to do the same thing in test set, because the train set structure and test set structure should be same before we pass the x value to the model, because the model is an equation of that many number of parameters. If you directly try to pass the train set to the model, right, it will fail, because there are values which are the categorical, there are nulls, there are all the exploratory data analysis and feature engineering's outcome on train set is not actually applied to the test set. So that's going to create problem. So we need to apply that. So lines of code issue we are fixing, and then we are dropping employee number, because employee number is of no use in predicting. Years of salary is actually we are replacing it with years of salary impute value. Do you remember this? We actually saved it somewhere here. Years of salary impute value, right? If you look at see this years of salary impute value, we have taken mode value from the train set and using that same value to impute test set. That's the right approach, because on train set you will have more data, and the central tendency there is more appropriate compared to test set, because test set is only 20% data. Whenever you are building a model, you should have, or you should get understanding on train set, and get that understanding and replace values or fix values in test set. In future we will see, on train set we always do fit transform. Fit will understand and transform will transform. But on test set we will do only transform, because the understanding is already there in the object and we'll use that understanding. This is the understanding here. Years of study impute value is the understanding we acquired from the train set. We are using that to replace it in test set, because the test set data is small, you shouldn't be understanding anything there. And one more thing is, even in production, while transforming, we'll use the same values. The train set understanding is the values you will use. That's the reason why the train set distribution or the train set sample should be more appropriate. If it is more appropriate, the understandings or the numbers we acquire from train set are going to be more appropriate on the test set and production. Those are the values we are going to use and replace, and then make predictions. I hope you got the point, right? The years of study impute value, qualification impute value, degree impute value, and educational institution impute value, all these values are being captured from the train set because the data set is big and the train set is huge and the understanding is better. We are using those values to replace the test set. This is how you should be doing. Okay, all the transformations we have done on the train set we are performing at the same time. The values captured, the central tendency values are the standard deviation values we understood on train set. We are bringing them and transforming the test set. Even the convert categorical method also we are using the same method. I am saying same method because if you go up and see, we have created a dictionary to find out the allowed values. On the train set you will have more all the categories covered, but in test set there is no guarantee that all the allowed values are covered. You are actually capturing 80% there of the data. There you may find all the categories, the records belonging to all different designations, but it is 20% only on the test set. You may not find all the designations there. If you try to create this dictionary again and try to impute or try to do the label encoding, well, the numbers would change, right? The number assigned to senior developer, the number assigned to analyst, the number assigned to senior analyst, these numbers will change, right? So we should use the same dictionary and same code to do the label encoding or one hot encoding. One hot encoding we'll see in future, right? So this is what we need to do before you test the data set, test the model on test set. We need to apply all the transformations which we applied on the train set, and then we should use all the understanding we have acquired from train set and use it and do the transformation. I have done it. Now the train set is ready, right? When the train set is ready, now I am splitting the train set into train X and train Y, vertically splitting, right? And now I will pass the train X to the model. See here in this flow chart, right? We are passing train X and predicting the values. Using these values, we'll again evaluate our model. See this here? I am predicting the values. I've got the test prediction. I've got the actual Y values of the test set. I've got the predicted values of the test set. I'm calculating R square score. If we haven't taken the 20% data set aside, we will not get this opportunity because in production we will not have the actual Y values. We may not have access to actual Y values. So on the test set, that is another advantage. Using test set, that's another advantage. So test Y and test predict we passed and R square score we calculated, mean square error we calculated. If you look at it, it is working better on test set, 66%, right? So it is kind of, I can say it is kind of equal because the data set is small. We can, a little lenient on the scores. The model is not working either on train set or on test set, but generalization is same. It is not overfitted. It is underfitted. Okay. So in the next session, we'll try to understand where the problem is. Whether the algorithm was unable to understand the pattern or data is insufficient to understand the pattern. When the model is not working or when the model is not working on the train set itself, there may be two problems. One, the algorithm is weak in understanding the data patterns, or the data is not sufficient. The amount of data which is provided to the algorithm is not sufficient in understanding the pattern. So we need to understand where the problem is and then we should solve the problem, right? If the data is insufficient, we need to collect more data. If the algorithm is insufficient, maybe we need to complicate or make the model a bit complex or try to find an algorithm which is more complex than whatever the algorithm we are using, right? So we'll see that in next session. Thank you.